Right, thank you. Good afternoon, everyone. I'm going to give a talk about acceptance criteria in fire safety engineering. It's a little bit about the review that we did and also a bit about the case study that we have performed. I can start by acknowledging my colleagues who I did this paper with. It's Carl Friedolf and Andrew Purchase, and my apologies, Andrew, for misspelling your name on my front slide. This is going to be on YouTube and everything. But I'll give you a bit of some background information before I move into the case study that we did. So when we are verifying fire safety engineering, we usually rely on three different methods: qualitative methods, scenario-based methods, or risk-based methods. When it comes to verifying safe egress, we usually tend to use the scenario-based methods. So during this talk, I will start comparing two different approaches to scenario-based methods. One of them being the traditional AZ/RZ analysis, and the other one being the concept of introducing fractional effective dose FED values. A few words about the two methods. The traditional AZ/RZ analysis, I wouldn't say that they are simple, even though I wrote it on the slide, but I would say that they are pretty straightforward. They are well known how to use. We use the fire model to find the available safe egress time at the AZ time. We evaluate the results from the fire model and compare them to absolute values, design criteria. Then we do some runs in some evacuation model to find the RZ, and we compare the two values. The fractional effective dose concept is more common when you evacuate through smoke. It's a much more complex method. I will go into the details in a bit. We use the fire model, like a CFD model, to calculate concentrations of different species, and we use the evac model to calculate the dose that people are exposed to. I will start discussing a little bit about acceptance criteria for absolute values, the type of criteria that we apply to the traditional AZ/RZ analysis. And I can start by mentioning that when we did the review here, we came to the same conclusion as Bill Cauffield did during the Gold Coast SFP conference, that there is no uniform set of criteria in the global perspective. However, there are several documents stating acceptance criteria for absolute values. I would like to highlight two of them, them being the Swedish building regulations and the New Zealand building regulations, since they actually have tenability criteria mandated in the building regulations. I can also mention that there is some European initiative to gather acceptance criteria within Europe, but still there is quite a big variation between the different countries in Europe. This table here indicates what typical acceptance criteria could look like when we verify against absolute values. You have the criteria, the different parameters here in the first column. The second column states what the acceptance criteria is in the Swedish building regulations, and the third column what the acceptance criteria is in the New Zealand building code. And typically we have, you look at the smoke layer height, which in this case is a function of the ceiling height. We have criteria for visibility, both for small and large spaces. There is criteria for long-term thermal radiation exposure and also short-term thermal radiation exposure. There's a temperature criteria of 80 degrees Celsius, and there's also some concentrations criteria for carbon monoxide, carbon dioxide, and you shouldn't, and the oxygen availability should also be above 15%. Comparing it to the New Zealand building code, we have the same visibility criteria. However, when we study temperature and carbon monoxide, they tend to use FED values instead, FED thermal and FED CO. And the criteria for that is 0.3 in both cases. To summarize these acceptance criteria for absolute values, I would say they're quite simple to work with, easy to evaluate with your fire model, and very important, they generally have quite low sensitivity to changes in the combustibles, which will be a major factor when we compare the results to the FED concept instead. And I would say that they're also quite well accepted in the community. The required inputs when we do the AZ/RZ analysis is typically the fire size, the growth rate, the CO yield, CO2 yield, soot yield, and heat of combustion. Now, moving on to FED tenability acceptance criteria, we do have some design situations that require alternative measures to assess the consequences of a certain fire scenario. This especially when we evacuate through smoke, like in tunnel systems, road tunnels, rail tunnels, metro systems, or even sprinkler buildings. The big difference here is that comparing to the absolute value criteria, it's much more common that the responsibility lies with the designer to assess, first of all, which methodology to use, secondly, which gases to consider in your analysis, and third, what is the acceptable accumulated dose to verify life safety against. So it's a much more complex problem, and as an engineer, there's probably a bigger risk to the project since you have to find all of these parameters yourself. Here are a few common values that you can see in the literature when you do a review on FED values. Commonly, you study either FED value less than 1 or less than 0.3. An FED value less than 1 means that 50% of the population exposed to it will start showing signs of being affected. While when you calculate FED less than 0.3, it's more like 11% of the population showing signs of being affected. The difference here is that you have to input more yield data into your analysis. If you want to account for toxic and narcotic gases, these type of gases are usually highly dependent on the fire situation. And what I mean by that is that they are dependent on the ventilation conditions and temperatures, among other parameters. And from what we found when we did this review is that this is really difficult. It's really difficult to find reliable information since it's seldom reported, or it's for some very specific scenarios that are difficult to apply to your case. So in this paper, which is a review and a case study, major part of the review actually went into this, finding reliable data for yields of different gases. So when we started writing this paper, we started thinking about a purpose, and the purpose here is that we wanted to investigate the consequences of applying different methods and different acceptance criteria to verify fire life safety. We stated 3 goals that we wanted to reach. The first one is that we wanted to know how the fire safety outcome is affected by the method use. And by this I mean whether we use absolute values or FED, the FED concept. Secondly, we wanted to know how the fire safety outcome is affected by the acceptance criteria that you pick. And as a third parameter here, we also wanted to address the challenges you face as an engineer when using the 2 different methods, more from a practical point of view. So the method we used to answer these 3 questions is that we used a case study. So the geometry for our case is quite simple. We picked the IMO test case number 10 since we didn't want to introduce any unnecessary complexities into our model. We want to keep it simple. For those who aren't familiar with the test case, it's a typical cabin arrangement of a passenger ship. There are 12 cabins in here, 23 occupants. And the dimensions here is that each room is 3 meters, so I guess it's 18 meters by 11 meters, something in total. There are 2 exits, one here and one there. But we didn't consider any movement at all in our model. We figured people are sleeping here. We only wanted to run the fire model and look at the exposure to the sleeping people in here. I'll touch by that in my conclusions later on as well. We used FDS as a fire model. The grid size ranged from 5 to 10 centimeters over in the model. We had openings at the escape routes to let air into the model and relieve the pressure. We put the fire source in cabin number 9, since it would affect both escape routes. It doesn't really matter. Each green point here is a measure point that's located 2 meters above floor level, and it records different data, such as visibility, smoke layer height, different concentration of species, temperature, etc., etc. So for this geometry, we applied 2 different cases. The first case is taken from the Swedish building regulations, and I will refer to them as BBR AD. That's what the regulations are called in Sweden. So this is input data that is mandated by the authorities in Sweden. So it's pretty straightforward. You just pick the numbers out of the regulations and put them into your model. We use a 5 megawatt fire that has a fast growth rate, heat of combustion of 20, soot yield of 0.1, carbon dioxide yield of 2.5, and carbon monoxide yield of 0.1. There are no additional species added to this case. The only species is soot, carbon dioxide, and carbon monoxide. The second case, we wanted to add more species so we could highlight the effect of the fractional effective dose here. So we did quite a literature study, and we came up with this sofa that the NIST has burned sometime, and where they measured lots of other species. So the difference here between the 2 cases is that we add all these. We add hydrogen cyanide to the model, hydrogen chloride, nitrogen dioxide, acrolein, and formaldehyde. We didn't have data for the heat release rate, etc., so we just used the same data as we did from the BBR AD case. So that means that we have 2 fires that have the same heat release rate, the same growth rate, etc., the same soot yield even, but there is a difference in carbon dioxide yield, there is a difference in carbon monoxide yield, and the NIST SOFA case also have these additional species. So that's a big difference between the 2 cases. So wrapping it up and looking at the 2 cases, our BBR AD case is a very well-defined case taken from the regulations. Both the input data as well as acceptance criteria is in there. We deal with carbon monoxide, carbon dioxide, and soot. Since we only have C, H, and O atoms in here, we can use the simple chemistry in FDS. Compared to the NIST SOFA case, where we introduce chlorine here, we have to switch to the complex chemistry model. Using the complex chemistry, all these additional species that I mentioned, they were lumped in the model to keep down the computational time. The volume fractions were calculated from the stoichiometric coefficients of the primitive species. I wouldn't say this is a big deal, but it is a bit more complex. You have to balance some chemical equations and so. It can be done, but it introduces a bigger complexity when doing the modeling. So looking at the results, I'll try to explain what we see here. On the x-axis are the different cabins. That's banded here. See cabin 12, 11, 10. Cabin 9 is our fire cabin. On the y-axis is the time at different parameters exceed their acceptance criteria. And all the different triangles and squares in here are different tenability criteria, different parameters. So looking at the BBR AD case, our well-defined case without all these additional species, we can see that the smoke layer height and the visibility is the parameter that is lost first. It's down here. In the fire room, we also lose the temperature criteria and also the thermal radiation exposure criteria. The temperature criteria is also lost in 2 of the nearby cabins. In excess of this, the only other parameter that exceeds its tenability criteria is the FED value when it's less than 0.3. And the difference between exceeding the visibility value and the FED less than 0.3 value is in the range of between 4 to 8. So there is a time factor of 4 to 8 between ASET when studying these two parameters. Other values, such as concentrations for carbon monoxide, carbon dioxide, FED less than 1.0, and also the fractional incapacitating concentration, which is a parameter that can quite easily be derived from a FDS, they didn't exceed their critical values at all during the simulated time. Now, moving on to the NIST SOFA case, things start to look a little bit different, but we do also see some similarities. First of all, smoke layer height and visibility is the same as in the BBR-AD case, which is expected since we use the same soot yield in the two cases. Temperature data and thermal radiation data is pretty much the same as well. Then there are a few things to note here. First of all, the red triangles, the fractional incapacitating concentration is exceeded more or less at the same time as poor visibility. And this sort of makes sense because the acceptance criteria of 1.0 doesn't mean that incapacitation occurs. Actually, you have to reach a value of 3 to 5 in that range to be incapacitated, which makes sense since poor visibility won't make you incapacitated either. Another thing to note is that the scale on the y-axis is the same as in the BBR-AD case, and you can see that the black triangles and the yellow triangles, they have moved downwards quite a bit. And these are the FED values, black meaning less than 0.3 and yellow meaning FED less than 1.0. And this is more obvious when I put the two graphs on top of each other. So looking at the black triangles, you can see that they are definitely moving towards this, the results for visibility when we add all these additional species. So there's quite a substantial difference between the two cases here. And in the BBR-AD case, we didn't even reach tenability with FED less than 1.0, but we did with the additional species in the NIST fire SOFA case. So trying to answer the questions I stated, how the fire outcome is affected by the method used. Well, first of all, impaired visibility is the tenability criteria that's first exceeded, which is expected. Of course, it's what we usually learn from doing ASET-RSET analysis. Using fractional effective dose will buy you some more time, because at least in this case, for all cabins, the FED as a criteria will always allow for longer ASET compared to the using absolute tenability criteria. The difference was 5 to 8 times longer without the additional species. When I added all these other species, the difference was much less. We could also see that the fractional incapacitating concentration less than 1 more or less matched the visibility criteria. And actually, the fact is that as we added more species, this simple model, the traditional ASET-RSET model, became a pretty good indicator of when tenability occurs. I mean, we get more or less the same results, but there is a huge difference in effort between the two methods used. So second question, how the fire safety outcome is affected by the acceptance criteria. Well, first of all, when we studied visibility, we had two criteria, 5 and 10 meters, and they were more or less exceeded at the same time, which I guess is due to that we have more or less of a two-zone model in our geometry here. From the literature, you can see that there is a range of layer height that you study as a criteria, but I wouldn't say that would have much of an effect. We didn't look much further into it in our study here. For the BBR-AD case, it's difficult to say something about the fractional incapacitating concentration or FED since they were not exceeded. But as we added all these additional species, the FIC value was the first one to be exceeded. It took approximately 1 minute, then the FED less than 0.3 was exceeded, and it took yet another minute, then FED less than 1 was exceeded. And finally, what challenges would you face as an engineer? Well, applying absolute tenability criteria to a case, I would say it's pretty straightforward, especially if you have mandated input data and acceptance criteria as we do in Sweden and New Zealand. Using the FED concept is much more difficult. There is no uniform agreement on acceptance criteria. There is no uniform agreement on which species to add. And it was for us very difficult to find reliable data, which is a big part of this study. And also the complex chemistry that you have to introduce might introduce a greater risk of user error as well. On the good side is that the tools that we used for this study, they worked very well, especially FDS worked like a charm. So thank you, NIST, for that. We didn't do any evacuation modeling here, but if we would have incorporated movement into this model, I would have picked an evacuation model that accounted for reduced walking speed in impaired visibility, since that would affect the dose quite a lot. So I'll pass that one on to you, Thunderhead guys. And that pretty much wraps it up. Yeah, thank you.
Any questions for Daniel? Can you talk about what kind of ventilation or how you account for the leakage to allow the products of combustion to be distributed through the cabins?
Oh, I think just that we left the doors open. And we had openings for fresh air at the exit routes. Yeah, I think they were the door width times 0.6 meters to introduce air to the model and relieve pressure.
Any other questions?
Thank you, Daniel. You mentioned that New Zealand code also looks at FET, like thermal FET, so the accumulation of thermal. Do you look at it as well? Because the FET you show was the one coming from the species, but not on the thermal?
Exactly, species. No, we didn't study thermal FET. We didn't.
Okay. And the second question is that the FET is an interesting indicator, but as well, it has some, I wouldn't say uncertainty, but some, when we said FET equal 1 and 50% people being affected, when you look behind those figures, actually there is a log normal distribution put in there just by consensus, I would say. So I don't know, what is your feeling as well on the robustness of the FET indicator?
Difficult. I haven't worked that much with it, so I feel actually I lack experience to answer that. Don't know. Sorry.
No, thanks. It was more like the general.
Yeah. Fine.
I think we had one more question.
Yeah. Thank you. What if the fire started at cabin 12 instead of cabin 9, since you left the doors open?
We will probably get different results, but I don't think it's. I mean, this is just one case study. It's not. I'm not trying to draw any general conclusions from here. The only general conclusions that I want to draw is actually what you can learn from the engineering perspective. Otherwise, it's all related to the case that we picked, which is a simple case.
Yep. Thank you.
Any other questions? All right, thanks again, Daniel.
Sure.